Hi, I'm Randall Heyman, a university mathematics academic. Welcome to my Corona Help playlists, where I make quick turnaround videos for students, educators, and in some cases parents during the coronavirus outbreak. So if you'd like me to make a video for you, just comment below any of my videos or drop me an email at coronahelpmathematics@gmail.com. Okay, so I got a comment below my video, Modular Inverse Made Easy, which I did a few years ago, from Eduardo, and he said he was not sure about step 2, and I've actually had quite a lot of people querying step 2, so this will be a good chance to do it. So I'm going to try here. Here's the video when we got up to step 1. So we were trying to find here, you can see here the GCD of 3,197 in this step. And what we did was we used the Euclidean algorithm, where we start up here. We work out the remainder. This is the remainder here when we divide 3,000 by 197. And then we use that remainder of 45 here to then, we repeat the process, and we just keep repeating the process, and eventually down the bottom here we get 1. And that's the GCD of 3,197. If you're unsure about any of that, have a look at, I've got another couple of videos. They're actually both the same. One's called Greatest Common Divisor Made Easy, and the other one's called Euclidean Algorithm Made Easy. And that will go through that. But Eduardo's problem was really the next step. And really the next step is about getting to this. Let's put this up here in, let's put this up in red, even though it's going to not look good against the green background, but whatever. So the task here is to find, in step 2, so here's step 2, find A and B such that 3,000 times A plus 197 times B equals 1. Okay, so the 1 that I just mentioned, that comes from down here, because 1 is the GCD. So what this is saying, and this is Bezout's identity, this is saying that the GCD of any two numbers can always be expressed as some multiple of the first number plus some multiple of the second number. Now, obviously, in this case, one of the A or a B are going to be negative. That's fine. That's no problem with that. So let me just try and rub out some of all these little marks I've put. Okay, so Eduardo was not clear about how we do that. So let's have a go at that. So basically what we do is we do the extended Euclidean algorithm, and we basically start here, down the bottom here, and work our way up. So let me just go through this nice and slowly, and hopefully it all will be clear. So the first thing to do is we use the last line. Use the last line, which I'll just put that there. So I'll put here, just so there's no confusion about what the last line is. Okay, so the aim here is to express, if we look over here, the aim is to find a multiple of A and B, or multiples of A and B, which when added together give 1. So I'm going to use the last line. I'm going to start by putting the 1 here, 1. So, because 1's what I want. So, okay, 1, what is that? Well, it's, because of this line here, I can say 1 is equal to 6 minus 1 times 5, which is pretty obvious even to a primary school student. But what have we actually achieved here? Well, we've expressed 1 as a multiple of 6 and a multiple of 5. Well, that's not what we want. We want a multiple of 3,000 and a multiple of 197. So we've got to somehow get rid of this 6 and this 5 to get what we want. So how do we get rid of the 5? So next step is get rid of the 5. So how do we get rid of the 5? Well, here we've got an expression for 5. So I'm going to call this dagger. Okay, get rid of it. Use dagger. Okay, let's use dagger. 5 equals 11 minus 1 times 6. Okay, so I've now worked out a way to express 5 in terms of 11 and 6, which doesn't sound like a lot, but it means I'm making progress. I've got rid of the 5, which was the lower of the two numbers, 5 and 6. I've worked out a way to express it in terms of bigger numbers. So I'm heading towards what I need. So let's just write up what we need to do here. I'm going to call this equation, I'll call this equation 1, and I'll call this equation 2. So substitute 2 into 1. Okay, so what do I get? I get 1 is equal to 6 minus 1 times. Now, instead of 5, I'm going to put a bracket, and I'm going to put 11 minus 1 times 6. And when I work all that out, what have I got for 6? I've got a 6 minus 1 times minus 1, 6. So that's 2 times 6 minus 1 times 11. Okay, so we have actually made some progress. We've got rid of the 5, and now we've expressed 1 in terms of 6 and 11. So now we want to get rid of the 6. How are we going to get rid of the 6? Well, we're going to use this one, because that tells me 6 in terms of 11 and 17. Okay, so now the problem is, what am I going to write? Where am I going to write this? Okay, well, I suppose I could get rid of this stuff now. I don't need 1 anymore, do I? I'm not sure how well this works. The arrays are on. Doesn't seem to work too well, does it? It's not great. Okay, so I need this equation down the bottom, but I don't need this. Actually, I don't need. So what I'll do is, okay, I'm doing this really nicely and slowly, because a lot of people have had problems with this. I don't need this anymore either. And in fact, what I'm going to do is, all I'm going to do is write this. Let me just write this up here. We now have sorry, I got rid of the 1 there. 1 equals 2 times 6 minus 1 times 11. Okay, and now if I want, I can get rid of this because I've written it up the top. Okay. Okay. So now I'll put here, get rid of 6, because we don't want multiples of 6 and 11. We want multiples of 3,197. So 6 is the smallest one. So I'll get rid of 6. I'll get rid of 6. Okay. So where am I going to find an expression for 6 that I can substitute in? Well, I've got this one here. So I'll call this, let's call this equation 3 now. And let's call this one, okay, let's just call this 4. So from 4, what do we have from 4? 6 equals 17 minus 1 times 11. Okay, I'll call that equation 5. So now substitute 5 into 3. So what do I get? I get 1 is equal to 2 times. Now I want to get rid of 6, so I'm going to put a big bracket. I'm going to put 17 minus 1 times 11 minus 1 times 11. And what does that equal? Well, I get 2 times 17, and I've got minus 2 minus 3 times 11. Let me just write this one in a bit clearer for anyone who's getting a bit confused there. And look, at any point, you can check that this is right. 2 times 17 is 34, minus 33 is 1, so it works. Okay, so what we've done is we've made a lot of progress. We want to express 1 in terms of 3,000, multiples of 3,000 and multiples of 197. And now we've expressed it as multiples of 17 and multiples of 11. Now, I don't think I want to go through the whole thing because it'll take too long. I like to keep this sort of reasonably short, these videos. So I hope now you can see the next step. The next step is, let's just change the color here. Actually, let me try this one, for example. We want to get rid of 11 now, which is there. So where are we going to get an expression for 11 to substitute in this to get rid of 11? Well, we've got one here. We know that 11 equals 45 minus 2 times 17. So we can substitute it back in here, and we know that'll get rid of 11. What's going to be the result? We're going to express 1 in terms of multiples of 17 and multiples here of 45. So at every step that we go back up the Euclidean algorithm, we increase the numbers that we're taking multiples of to get 1. And so eventually we'll get up to here and we'll have 1 expressed as some multiple of 3000 and some multiple of 197. Okay, Eduardo, I hope that's helped, and I'll probably put a note of this under my video, Modular Inverse Made Easy, so that people can have a look at this, because as I said, from time to time, I do get questions on it. If you've got more questions on what I've written, then by all means, comment or email me, and similar if you've got anything at all about mathematics during the coronavirus outbreak.